Hi, this is lecture number 7, and it is kind of short, but it's kind of narrow in the scope. We'll talk only about one problem that's called curse of dimensionality, but in general, we just will talk about high dimensional spaces. This topic is important, I feel, because it's all over the place anytime you work with the data or anytime you solve any problem with multiple parameters and multiple things to tweak or keep in mind or to change. And yet, usually this problem is kind of only briefly mentioned, and most of you, I'm sure, have heard of it before. And some of you maybe even think that you fully understand what's going on. But this hearsay, cursory look is one thing, but a solid understanding and intuition is another. So in this lecture, I will try with some help to go through the details of what is the nature of the problem, so you may understand better when you are applying your classifiers or dimensionality reducers or other algorithms, clustering, for example, to your multidimensional data. As I said, outline of this lecture will be just one topic, curse of dimensionality. Ooh, spooky. And you can see my lectures online already, my slides as I shared them. This lecture is in part based heavily on Chapter 9 of The Art of Doing Science and Engineering by Richard Hamming. The last slide of this slide deck contains direct link to Amazon for the book, and this blog post in Russian, sorry, but I've translated the parts. Let's look at this tasty ripe watermelon. You're in a market and you want to buy some watermelon, and you, of course, don't want much of this not so tasty rind, and you want more of the red flesh. So, which strategy should you use? How to choose a watermelon that has more flesh than rind? Let's first look at this beautiful one-dimensional watermelon slice. And this slice right now is here. So what if the rind is just 15% of the radius? So this is our center of the watermelon and 15% of the radius rind. So 15% of the radius, if we buy not a one-dimensional watermelon, but we buy a slice, a two-dimensional watermelon here, then 15% of the radius of rind turns into 28% of area. But in three-dimensional watermelon, this 28% of the area is 39% of the volume. So when you're buying watermelon, almost 40% of what you're paying for is something that you're gonna throw away, is the rind. So even though your rind is very, like in the slice, this thickness is very thin, it's just 15% of the radius. The total volume of the whole watermelon consists of the rind, and increase the rind just a tiny bit, and you probably are buying more rind than the flesh. So that's an example of what happens, maybe counterintuitively, but maybe not, we'll see, in multiple dimensions. Let's now consider this example. Let's go slow in order for you to trust the paradoxes or the conclusions of this, where our lecture will lead us, I am ready to go with Richard Hamming, who goes step by step in his explanations. So let's also start from the basics. So let's look at this diagonal in parallelepiped or in a cube, multidimensional cube, some structure. So this diagonal connects these 2 points, and it's D2. How do we, and we know X, Y, and Z, how do we find the lengths of this diagonal? Well, basically, first we find D1, and D1, as we know, is a square root of x squared plus y squared, just Pythagoras theorem, into D. But then D2 is nothing but square root of D1 squared plus Z squared, which together is simpler expressed as a sum of squares, right? So, well, let me simplify. X squared plus y squared plus z squared. So pause that video and think about how in multiple dimensions and further dimensions, this diagonal, the distance of that diagonal is nothing but sum of all of the dimensions squared, each of the high dimensions. That should be clear, but we better look at it from the basics. So if it's not clear, make a pause and then continue to the next slide. So for the next slide, we start from somewhere unusual. We'll start from Stirling approximation for n factorial, and we'll use trapezoid rules for that approximation. We will derive it from scratch, so you know, like you're not afraid of it. So when we work with n factorial, it's kind of unwieldy, multiplying all of that numbers and then trying to analytically manipulate it is a little annoying and hard. So let's take a log of factorial, and then we can write a log of factorial as just a sum of logs of each elements in the product. So just intuition leap, sum is related to integrals. Let's look at an integral and see what we can do. Instead of the sum of the logs of the number, let's look at an integral, definite integral from 1 to n of log x, natural logarithms in x. Now we want to integrate that logarithm. Let's see, we can integrate this logarithm using something called integration by parts. So this is a tedious lecture. We want, okay, I want you to see every step so you trust this completely. When you see the conclusions, you don't say like, oh yeah, that's an interesting magic, but I don't know where it's coming from. So we will have to start from somewhere though. And let's start from assumption that you know the product rule for derivatives, right? It's u dv plus v du. Then so something like that. Now let's integrate both parts. E equal is when we integrate both parts, we can see that, well, antiderivative of derivative, uv, is still u dv plus integral v du. And from that, we can see that u dv equals uv minus integral of v du. So we derived the formula or approach for integration by parts here. And with this in hand, we can use it to integrate this log x. Let me think for a minute. Just reproducing it, u dv equals up minus integral v du. So in this, touch off is not fully working. I guess yeah, I didn't write that fully down. Let's say that our u here is log x, and dv is just dx, and then if our v then is x and our du is 1 over x dx. So using this formula, we can just plug it in, u times v x log x minus integral of, and we know that we're doing the definite integral, 1 through n, so we get, and this is 1 through n. If we plug 1, this is log of 1 is 0, so we will get n log n minus n plus 1. I believe so. Let's check my notes. Yes. So we integrated this definite integral, and we got this expression. Now let's look at this integral differently. Let's try also integrating it numerically. And numerically, we will integrate it using trapezoid rule. And trapezoid rule goes like that. So we are, like, this is a trapeze, and we know, or you can quickly derive that, is a plus b divided by 2 times h. So h, so this length is a, this length is b, and so if this is 1, 2, 3, 4, and so on, the h, the height of our trapezoid is 1 always. Let's get rid of that. And each trapezoid is 1/2 log I plus 1/2 log I plus 1. But then the next one is 1/2 log I plus 1. and so on and so forth. And that's why those sum up, but the ends don't sum to the whole logs. However, this is 0 because log of 1 is 0. And for this, we add a fudge factor to both sides. Yes. And rewrite the logarithm in the form that we just obtained. So the integral of the log x we just calculated, and then because we added 1/2 log n to both sides, what we see that on this side, when we did so, we just have sum of all the logs equivalently, because log of 1 0 and this is 0, it will be the same. And we got this formula, this expression. Beautiful. Let's now exponentiate both sides. And once we exponentiate both sides, look at this. This is nothing but n factorial, and it's proportional to the following expression. You can follow through by exponentiating all of those elements here. And this factor c is actually the this error that accumulates because of the trapezoid rule. It's not matching the logarithm completely, but we can show that it asymptotically approaches a number. So we're not going to derive here that number, just let's save time, but this number is square root of 2 pi. And we got our Stirling approximation formula for the factorial. So how does that formula work and how good is it? So let's look at the first 10 examples or first 10 numbers. This is what Stirling's formula gives us, and this is what is the true value. And for you, for convenience, the ratio between approximation and the true value is in this column. Notice that as n grows, the ratio goes to 1. But at the same time, the difference also grows. It keeps growing. So the difference becomes larger and larger, yet the approximation becomes better and better. We can look at an example, similar field, to get a similar field. If we have f of n equals n plus square root of n, and g of n equals n, then as n tends towards infinity, the difference of f of n minus g of n grows indefinitely, yet the ratio goes to 1 as well. Right? When n grows, this ratio goes to 1. Okay. Now we will need gamma function. So just a note before we continue with gamma function and everything. What I'm doing is I'm leading you through every step that will further, all of the steps will combine. So you're not surprised where gamma function comes from, how we derive it, why did we integrate by parts, and what happened. So let's look at gamma function because we'll need it for the volume of a sphere later. But as long as you understand what I'm showing you in the moment, please be comfortable that it'll all make sense further in the lecture. So gamma function is defined as this definite integral from 0 to infinity. Notice that the integral integrates over x, but gamma function is a function of n. So we can actually try and integrate this ourselves. And I think after Stirling's approximation, you get a feel of how to do that, right? Should be easy. Let's integrate by parts. Yes, by this slide, you are already a professional integrator by parts. And of course, I'm not making fun of you. You all have learned it previously in your calculus classes, but must have forgotten by now. Well, or there are some heroes who practice integration by parts every day, possibly. But okay, you don't need to remember anything. It's just must be clear. We just derived this formula, right? So you're super comfortable. And for that, let's denote u is x power n minus 1, dv is this whole expression, e power x power minus x dx, and then in this case du is just differentiating this x power n minus 1, and v is minus e to the minus x. So with this in hand, we can clearly rewrite this or integrate at least partially this definite integral as the following. So, okay. Okay, good. If you plug 0 here, both of the part, like this turns into 0 when you plug 0 because x is 0. And if we plug infinity, this turns into 0 because 1 over infinity yeah, okay, phew. Just yeah, if you plug infinity, well, I'm faking it, of course, because it's the limit of this expression when x goes to infinity minus e minus x. Yeah, now my calculus gears are lubricating and I even recall some of it. Yeah, so limit of that tends to 0. Just trust me on that. So this part goes to 0, and we have this expression. Some kind of weird and is looking familiar. Yes, it is familiar. What? Look over here. If n is n minus 1, then it's a gamma of n minus 1, right? This integral, nothing but gamma of n minus 1. And indeed, uh, this function is gamma of n minus 1, and we got sort of a recurrence relation. Gamma of n is nothing but gamma of n minus 1 times n minus 1 with a base case of gamma of 1 equals 1. That gives us correspondence that gamma of n is factorial of n minus 1. Okay, we derived a gamma function, a useful one. The advantage of gamma function for our purposes, I'm not going, it's not a mathematics course, and I'm not going into details of all of the derivations or proofs of consistencies and everything. But the importance for gamma function is that it can calculate all of the factorial numbers, but it is also continuous. It can, that's probably wrong, but it can calculate fractional factorials as well. not just integer factorials. And we will need an important fractional factorial for our next story is gamma of 1/2. How do we compute gamma of 1/2? That's why we need it actually, because the trick or technique of computing gamma of 1/2 will be important in the further exposition. Just plug 1/2. Remember what was here. Sorry about that. Remember what was here. Gamma n minus 1. We plugged 1/2. And this became x minus 1/2. So that's how we've got this integral. You know probably what's coming, right? We're going to do some substitution and make it interesting. So if we set x to t squared, then dx is, well, the differential is 2t times dt. And then we can rewrite this integral, the top one, as 2 goes over here. X is t squared, so we plugged it. So basically plug t squared instead of x in both places, and plug dx, or 2 times t dt instead of dx into here. This replaces that. T squared replaces this. You get this expression as a result. Okay, I hope you can pause it and do it on paper, but this is simple algebra. You can do it. I'm sure it's not even like obvious or whatever elementary. It's not my point. Is that you can easily plug it in and compute for yourself. But now see what is happening. This is two definite integrals from 0 to infinity, but that's the same as an integral from minus infinity to infinity, at least in this case, because, well, first one, t squared. So all the negative numbers here will have exactly the same value as the corresponding positive numbers. So now, what is t squared? Like, what does it remind you? T squared can be expressed as a circle, and this gives us a circle, right? Sort of constant radius from the center, which is t. So let's do the following trick, or apply the following trick. Let's multiply the integral by itself, basically. So we're squaring it, but we're squaring it in two different dimensions. One is in x and one is in y. That's how we replace t squared by familiar equation of a circle. Now we need to integrate that. How do we do that? Well, first notice that this looks very similar to, like, it reminds us, circle should remind you of a polar coordinate system. When you have a circle expressed as x squared plus y squared equals r squared, well, t squared, you can always express it in polar coordinate system as the radius and theta, the angle. This is how it will look. Still, gamma squared of 1/2 will be a definite integral full circle from 0 to 2 pi. So we're integrating from 0 to 2 pi. Yes, converting it to a polar coordinate system, we have turned we have turned this expression into r times e to the minus r squared. So outer integral is easy to calculate, right? It will be 2 pi, the full circle. And interestingly, the inner one is also easy to calculate. And you can do it yourself, but so what is antiderivative of ER? Okay, what do I have here? Let's calculate this. So we can easily calculate this antiderivative, because if you differentiate this, you will get 2 minus 2r over 2 e minus r squared dr. Okay, and there was this minus, so plus plus blah blah, and that's how you get this part that's here. So okay, we now know that it's minus 1/2 e minus r squared. Yeah, sorry, baby steps, but I don't want you to. It's like always useful when you're doing something to start from scratch to get a feel and conviction that this is actually what's going on. And then if you plug 0 here, then it is minus 1/2. And if you plug infinity, it goes to 0. So minus 1/2, 0 minus 1/2. So you get 1/2 here. And integral, the outer integral is just 2 pi. So then gamma squared of 1/2 is just pi. Right? I hope I was going slow enough. So gamma squared of 1/2 is pi, and gamma of 1/2 is square root of pi. Bear with me, we're getting somewhere. So now we know what gamma of 1/2 is. We know, and we're totally comfortable with what gamma is. And we're ready to calculate the volume of a hypersphere. So if we start thinking about a sphere, and I'm checking my notes, by analogy with a cube, right? It's easy to, I hope it's easy to generalize that, okay, if we have one-dimensional cube, the volume is 1. If we have two-dimensional cube, the volume is, well, let's call this dimension, because cube of characteristic dimension 1 is always 1. But let's say this is R, and then in one dimension it's R power 1, in 2 dimensions is R power 2, in 3 dimensions is R third power, and it's easy to see that the more dimensions you just get R power n, right? That's for the cube. But what happens with the sphere? So with the sphere, we can sort of intuitively guess that it also depends on radius power n, but with some constant in front. And think about one-dimensional sphere. So what is a sphere, first of all? Spheres is like all points that are equidistant from central location, some central location. So if our central location here in 1D, so all points of radius R, so as you can see, C1 equals 2. And then we know that in 2-dimension, it's pi. So volume of the sphere in 2-dimension, which is just an area, is pi r squared. Volume of the sphere in 3 dimensions is 4 pi over 3. But what is the general form of this constant? What is it? Let's derive it. And let's start with the following intuition approximation of a volume. If we need, and imagine this is a multidimensional sphere. So the volume of a multidimensional sphere is nothing but a sum of areas of the shells, all of the shells. So we're going, so if this increment is infinitesimal, then sum all the areas of all of the spherical shells and you get a volume of this sphere. But that means that sphere area is, because it's an integral, right? Area of the sphere is nothing but derivative of the volume by dr. So if our surface area is derivative of the volume, look at that, and we know this is constant and it's independent on it's independent of r, but we differentiate with respect to r in simple rule n times c sub n r power n minus 1. This is our surface area. Now, when we know the surface area, we can write an element of the volume as the infinitesimal element of the volume as a derivative of the surface of the volume, so surface area times dr. So this is our element of the volume. But then let's do a little trick in our gamma in polar coordinates. When we calculated gamma 1 over 2, remember we had r e to the minus r squared, where basically r dr was our element of the volume. The volume in this case was 2-dimensional. So, oops, pardon me. Okay, anyways, so e to the r squared. RDR was our element of the model volume, and this we're replacing this element of the volume because now it's n-dimensional. It's not 2-dimensional. Our polar integral absorbed all of the dimensions, remember, or absorbed the 2 dimensions. So our dimensions are absorbed here. We're integrating still from 0 to infinity, but now our gamma of 1/2 is power n. And since we know gamma squared or gamma was square root of pi, now when we raise it to power n, we get what we get, just that. Now going step by step, we know that derivative of the volume is our surface, which is here. Oops. So let's plug this into here. Take the constants out, rearrange, and what happens here, we also make some a substitution again, as we've done before. We substituted our square with t. So when we substitute our square with T R to the, so Rn minus 1, so then T, that's how the n over 2 minus 1 comes because of this substitution. But then this substitution goes with T. That's clear. Okay. And I was just thinking where Cn n over 2. Okay, dt dr, that's dr substituted with dt, that's where we got 1/2. Okay, so after this substitution, we got a new integral, still should equal the same value. But then we observe that this integral is nothing but gamma of n over 2, this part. Since this is gamma of n over 2, Cn of n over 2, gamma of n over 2. But this is the same, as you know, as gamma of n over 2 plus 1. That's where this comes from. Well, why did we do that? Well, we knew how to integrate the gamma function of 1/2. But we also knew that surface and volume are connected, and both include surface of a sphere and a volume of a sphere are connected, and they both include this constant c over n. Now, when we have this expression, we can derive or just rearrange and compute expression for c sub n, our constant which we need for the volume of a sphere, of hypersphere. So then our hypersphere volume, just rearranging of what I wrote there, will be this, and pay attention just to this now. So we have an analytic expression of this constant as a function of dimension. So let's go for a few dimensions, for 10 dimension, and look what happens with our coefficient of the volume of the sphere. So this is our flat sphere, this is our circle, this is our ball, and 4-dimensional, 5-dimensional hypersphere. Look what happens. First, it grows, but then it starts falling down. Yeah, this is the maximum somewhere here. So our constant volume of the sphere changes as follows, and eventually we'll figure out that for even numbers of dimensions, it's nothing that pi to the kth power over k factorial, but as k grows, it goes to 0. Ta-da! For a fixed r, not surprising that with fixed radius sphere, with growing dimension, the volume of the sphere tends to 0. Think about it. You're just increasing dimension. By increasing dimensions, you're sort of adding more room, but as we just derived, and you can recheck back all and every step that we've gone through, the volume of a hypersphere goes to 0. But surprisingly, if we rewrite for any arbitrary r, if we write n as 2k, like you can see here that no matter what R is, for any fixed R, as k goes to infinity, the volume of a sphere also goes to 0. Like R doesn't have to be, like R can be anything. So in a general hypersphere or hyperwatermelon, the ratio between the rind and the total volume is the following. So let's look at this. So we have the internal radius and external radius. And let's normalize our external radius, or let's compute this part. This part is nothing but r times 1 minus epsilon. This is our smaller radius. So then we have two spheres, or two volumes, V1 minus V2. So this is the outer sphere, this is the inner sphere, and normalized by the outer sphere. So that's how this formula is derived. Cn r to the n minus c minus Cn r 1 minus epsilon to the n, right, for n-dimensional volume. But that's how we get this formula. So Cn's go away, as well as r to the power n, and the ratio of the volume of the outer shell to the volume of the whole surface of the whole sphere is the following. Notice a paradox or sort of counterintuitive. So R here is the same epsilon. It's the rind in the watermelon. Let's notice that no matter how small the R is, this number is always smaller than 1. So we're getting 1 minus, I don't know, something to the power n. And as n tends to infinity or just grows, our volume, our volume of that outer shell equals to the total volume, or in other words, all of the volume or most of the volume, almost all of the volume of a hypersphere is located in the outer shell, is concentrated in the outer shell, while the volume inside is empty. So two paradoxes. Well, you can see the same. This is proportion taken by Rind in percentage of radius, right? So this is when Rind is 15% of radius. By dimension 90, the Rind is taking up, what do you think, 95% of the hyperwatermelon. But if the Rind was 50%, then quickly it is taking almost all of the volume of the hypersphere is taken by the Rind. First paradox was that volume of hypersphere goes to 0 as dimension grows. And I hope it's not a paradox. You just saw it yourself. We derived it. But the second one is in large multidimensional spaces, almost all of the volume of the hypersphere is in the outer shell. We can look at a different plot now, volume fraction as a function of the radius, as a function of the thickness of the outer shell. So if our outer shell, if our dimensionality is 20 and our outer shell is just 25%, it's already taking up all of the volume. But if, say, our dimensionality is 5, even just 5 for 5D, if you're 60% of the thickness of the outer shell, 60% of the radius are taking up all of the volume, so this other 40% don't matter. That's one. How does it translate to something closer to Earth? Well, I mean, all of these multidimensional spaces is where we do research, and you should understand that this is very relevant to any data processing or data planning or multidimensional uh, parameter optimization, or any problem that you're solving that involves several variables, several factors, will exhibit those effects. So Gaussian distribution, you've seen this in our PCA lecture. This is multidimensional Gaussian. The paradox is that almost all of the, when dimension grows, it's totally unlikely for a spherical Gaussian to fall into the mean. The Gaussian sort of has a mean, right? And when we, in a one-dimensional Gaussian, the mean is most likely place for a sample to be drawn from. But if you go into two dimensions, and if you take a recall definition of probability, that it is actually an integral, probability mass is an integral of your probability density function. So if you integrate two-dimensional probability in this outer shell around most of the probability mass is in 2D, is concentrated at a radius, and this is a Gaussian with unit variance and zero mean at a radius of 0.5. And if you go into 20-dimensional shell, then most of the probability density is concentrated in that shell away from the mean around 2. So it doesn't mean any point here is like any other point. They're totally or very different because there are many more options, but they're all concentrating around the shell in this multidimensional space. Not falling into the mean is super, super, super unlikely. And mean is our average case, right? Okay. Look at this. What if the flesh isn't in the center? Let's go back to our watermelon example. I guess because it's tasty and it's easier to talk about watermelons. So what if the flesh is at a known position, we don't know where it is, and it's only 10% of the radius, the rest is rind? What is the probability of randomly hitting the red point? Well, it's 0.1, right? If you randomly sample in like randomly throw a dart here into one of the boxes, the probability is closer to 0.1. So, but in 2D, it's the same. What is the probability of randomly hitting the flesh if most of it is bad and only one place is good? But if we don't know where this good and tasty flesh is, what is the probability that we'll actually hit it by uniformly sampling within this area of a circle, right? It's 1% of the area. When the rind or when the flesh is 10% of the radius, it's just 1% of the area. So your probability of randomly hitting the sweet spot, this circle, is 0.01. Very, very low probability. Why is it important, or why should we care? Yeah, what's the probability of randomly hitting the flesh? Because in multidimensional optimization, and of course we resort to just two-dimensional, imagine that we're running our gradient descent, which we already discussed and spoke about, and there is this ball of sweet spot, and if you start randomly with random start anywhere else, when the function looks like that, you will end up in a bad solution in local minima. Well, in 1D case, say this is 20%, and the probability of hitting this is yeah, well, 20%, one half, wait, 1/5. If you randomly sample 1/5 of your starts, so throw in one dimension, throw 100 random restarts, uniformly random in this interval, and 1/5 of them, 20%, will converge to a good global optimum. But if you're in the same situation, well, in 2D space, right, it's much smaller number. So as we saw, the correspondence for 10% is one. Well, I'm probably messing up the exact number, but you get the point. Random restarts in multi-dimensional spaces, where we're always in multi-dimensional spaces. In the cases when our local minimum and our optimum or global minimum is like uh, taking up a basin of a small volume, thus random restarts are hopeless. I hope that's clear. Well, I don't know if you're convinced or not, but let's look at another example. There are way too many, and we still need to go through a couple. Oh, I guess this lecture is not so short or not too short, but I hope it's definitely easy to follow and interesting. So if we look in high dimensional spaces, then let's consider diagonal. Remember in our Pythagoras theorem, we had diagonal between two. That's annoying. That's not what I meant. We had diagonal between two furthest point. So basically we start at the origin and draw a line or a vector to this point. So if we compute an angle of this line with any other lines, or any other axis aligned lines, like there are two in this case. So cosine of that angle, it's I think I have it. The cosine of that angle will be 1 over square root of n. It's because the length of axis aligned vector is 1, while the length of this diagonal is square root of n, right? This is from the generalized Pythagoras theorem. So as n grows, cosine theta tends to 0. That means the vectors tend to be perpendicular. But there are, yeah, like it will be almost perpendicular, but it's not quite, but it tends to be perpendicular. So let's now look at another very interesting case. Let's randomly draw vectors from this distribution. Richard Hamming in his chapter 9 of his book derives this equation, but for us, we'll just assume that you all know that inner product of two vectors normalized by their length, x and y, the length is, in this case, the shortest distance from the origin. Well, usually the length is shortest distance as defined by something, by the metric of the space, but we'll see that in your homeworks tomorrow, I guess. So cosine is defined as inner product normalized by the product of the weight of the distances. So let's now sample from a specific vectors. They are all vectors of ones, but their signs are plus and minus randomly. So we have about 2 to the power n of those vectors, not about, but exactly, sorry, 2 to the power n of those vectors. And what we can show is that take 2 random vectors of this sort, and as n dimensionality grows, there will be this ratio, the cosine, and this n is xy because those vectors are all +1, -1. All of their lengths are square root of n. And when we multiply square root of n by square root of n, we get this n. So cosine theta between any random vector, any of 2 to the n random vector, will almost surely converge to 0 as n goes to infinity. So for in larger dimensions, almost all of those vectors, or large number of those vectors, will be perpendicular. Surprisingly, take random vectors and they will likely be orthogonal, perpendicular to each other, or at least perpendicular, almost perpendicular to each other. To illustrate that example, look at 2D. In 2D, we have a small tolerance of our precision, and vectors that are almost perpendicular to the vectors in this on this line, just a few. In 2D, the vectors that are perpendicular to this line grow, and you can continue that intuition. For large n, there is just a vast number of vectors perpendicular to any vector that you take. Like in linear algebra, in theory, they tell you find an orthogonal basis for any space. But once you found one orthogonal basis, there are almost 2 to the power n or 2 to the power d vectors that are also almost perpendicular to all of those vectors, even though you kind of fix the basis. So in theory, there is absolute perpendicular basis. But in practice of linear algebra, as soon as you don't have infinite precision, everything becomes very, very tricky because of this problem. So that's another paradox. Here's how we can look at it. So probability of orthogonality, this pi over 2 is about somewhere here. And in 2 dimensions, almost all vectors are distributed, like the vectors are distributed at any random angles. All of them, 0 over from 0 to 2 pi, yeah. But as your dimensionality grows, it's far, far, far more likely for any 2 vectors to be orthogonal. For dimensionality of 50, look, everything is concentrated in orthogonal space. Another example is, imagine that we need to estimate a probability distribution. So to estimate a probability distribution in this dimensional space, so what's the minimum number of samples we need to estimate d-dimensional density in a cube? So if we have, say, 1 sample per bin, that's the minimum that we need. So if we're looking here and trying to fake 3D, I'm being too creative, sorry. But that means a sample. So how many samples in total do we need here in order to estimate probability distribution? Well, number of bins to the d, n1, n2, right? So yeah, for characteristic dimension. So here it was, let's ignore this, was 3 samples. Here it's 9 samples, where n is now our discretization step. Or let's call it h. So h to 1 and h equals 3 in this whole example. This h2 will be 9, but this is 27. And for higher dimensional space, we need more and more samples. So imagine how many samples do we need in 50-dimensional space to reliably, well, we're not even talking about reliably, just a minimum number of samples to feed, to hit each bin. So that's what's called usually curse of dimensionality, that the required number of samples that we need grows much, much, much faster. And we can collect those samples. And then another example, just to kind of push that agenda further, that our intuition totally failing us in multidimensional spaces. Look at this simple drawing. It's a 4x4 square and divided into 4 squares, and inscribed, when we inscribe those spheres, their radii are 1. So those are radius 1 spheres. So what is the radius of this little sphere? Well, what is this length? This length is square root of d or square root of n, right? So for 2, this length is square root of 2. And the radius of the smaller sphere is square root of n minus 1. No matter how large is our dimension, how large is this n, the radii of this inscribed spheres are still 1. They don't change. But yeah, look what happens for dimension 2. R2 equals square root of 2 minus 1, which is 0.4, blah, 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 and so on. For 3, it's square root of 3 minus 1, which is 0.73, and so on. And what happens for square root of 10, for dimension 10? In dimension 10, it's already greater than 2. Look, the radius of this sphere is greater than this dimension. Well, it's easy to imagine, because if those spheres tend to corners with dimension growth, of course, a sphere that touches them pushes out. But that's not how our intuition works, right? For multidimensional spaces and converting this flat picture into multidimensional picture. Notice that. So from that, just a couple of more points. Everything, all those paradoxes, they happen with Euclidean space, the distance as defined in Euclidean space, and a sphere as defined in Euclidean space. We can define a sphere differently. We can define a sphere using L1 distance, which is just the sum of absolute values of all the coordinates. And this is L1 sphere, again, by definition. With respect to L1 distance, the distance from the origin to each of those points is the same. It's exactly the same. And we can take Chebyshev distance or L infinity distance when the max of the two absolute value or the max of each coordinate values is taken. And then this is the L infinity sphere. Each point on the sphere is equidistance from the origin with respect to this distance. This distance, both of them, they fit to different situations. For example, when we compare people with each other, we just use L infinity, usually just one prominent feature. Oh, who is higher than who? Just take the max. Or I don't know, like any other prominent feature. When we deal with more sparse values, like in binary codes, L1 is a really good metric. In what is a metric? Like when we can use a distance to replace L2, when we can still define the Euclidean space or space. It's when a distance or similarity is a metric, and there are a few conditions that it's good to know about what is a metric. So a metric has to follow has to be always non-negative. Non-negative, that means 0 or higher. Also, it has to obey this identity condition, such that if the metric is 0, the value of d of this distance function is 0. That means x and that means x and y are exactly the same. That they're equal to each other, and only then it can be 0. Only when they're the same. Another one is symmetry. So distance or between x and y is the same as distance between y and x. Another one, an important one, is triangle inequality. Is, well, you remember triangle inequality. The third side in triangle can be longer than the sum of the other two. And the last story, the practical story about all of that. So, like, how do we actually encounter this multidimensional spaces and make mistakes because we incorrectly think about them? Is the story from about 1950s. So after the World War II, there were still a lot of wartime planes left, and Air Force noticed that too many incidents and accidents were happening outside of the warfight, and they hired a statistician to study that. So the warplanes, fighters were built back then from average measurements of humans or of the pilots. So lots of pilots were measured, average height, average weight, average hand size, length, and that's how the ergonomics of the cockpit was designed. And well, the statistician, and I don't have the name now, done the following experiment, kind of irrespectively of the warfighter planes first, and because of that experiment, he was hired to do the job. So that was at Harvard. So you imagine back in the 50s, wealthy white male students. So he recruited 250 Harvard male students and measured 250 hands, and was trying to find a typical hand that is the average hand. And no single hand among 250 was typical. It's like we can calculate a typical hand, but we cannot find it. And by now, in this lecture, you already know why. Because all of the volume of a multidimensional distribution, Gaussian distribution, is concentrated in the shell, in the outer shell. Well, almost all, to be technically correct, but a lot of it. So for the warfighter planes, what he did, he measured just 10 features of 4,063 pilots, and those features included height, chest circumference, sleeve length, anything that yeah, anything that would fit the conditions or tasks of building the cockpit that they use for building the cockpit to make it comfortable for an average human. So for this 4,063 people, the researcher was trying to find for how many people all of these 10 features fall within 30% range of from the mean, from the average range. How many did he find? Right, 0. So this average metrics, average cockpits built for average pilots were built for no one, and they were uncomfortable for every pilot, basically. Okay, so, well, congratulations. Every one of you is unique, and no one here is average. And if we happen to find an average person, this will be also a very unique event, and this person will quickly become unique. Some of the literature that I used to prepare this lecture is here, and my bad, it wasn't so short, but I hope it was a light lecture compared to the others, and I hope you enjoyed the paradoxes of multidimensional space. See you in class.